Hello, and welcome back to our course on Descriptive Data Analysis. In this class, we are going to talk about measures of shape. As the name implies, these measures allow us to assess the level of thickness or flatness, the steepness, and detailedness of the distributions. It's very important to have this information in advance because, for example, if you know that a distribution has a tail, you know that this distribution has some outliers. And the longer the tail, the more distant are the outliers from most of the distribution. The measures of shape are very important because they bring information about the underlying data distribution, such as where the data is accumulated, the presence or absence of outliers, and if the distribution is more skewed or spread. To illustrate, we can look at these distributions here. We can see that this distribution is slightly steepened here in this part, but it also has a long tail to the right. This distribution, by contrast, is more uniform, so we have a more spread distribution, but we have no tails. And finally, this distribution here, it looks more like a normal distribution. It has some tails. The tail to the left is a bit longer than the tail to the right, and it's also very steep. Let's start with the measure of skewness. Skewness basically measures the asymmetry of the distribution, and this allows us to quantify the direction and the length of the tail. Positive skew means that I have a tail to the right, whilst a negative skew means that I have a tail to the left. Another important information that we can get out of this skewness is that a positive skew means that the mean is usually greater than the median, whilst a negative skew signifies that the mean is smaller than the median. And this relative position between the mean and the median is also an indication of the skewness of the distribution. Let's have a look at it in an example. Here I am plotting you one distribution with a positive skew and another distribution with a negative skew. I am also plotting the values of the median, the mean, and the midpoint. The same thing for this negatively skewed distribution. And remember that the midpoint is calculated by taking the both extremes, summing them, and divided by 2. Whilst the mean takes into account all the values of the distribution, sum them all, and divide by the number of values. And the median is obtained by ordering the values of the distribution and taking the middle one. Therefore, as the midpoint considers only the extremes, the midpoint tends to be much more sensitive to outliers than even the mean. And this is observed here. The fact that the midpoint is much more to the right means that this outlier to the right here is pulling the midpoint in its direction. The fact that we have an outlier with a very small value in relation to where we have the more accumulation of values in my distribution forces the midpoint to move more to the left. If we want to have a look at the numeric values, here we have the numeric values for the mean, median, and midpoint of this right skewed distribution. And we also have the skewness calculated by this coefficient. And it's important to realize also that we have different ways of calculating the skewness, and this is the one that is most commonly used by the tools that we work with. The left skewed distribution has this mean, median, and midpoint. As we can see here, the mean is approximately 0.8 something. It's 0.83. The median is 0.86. And the midpoint is 0.57. The skewness is negative. The fact that the skewness is negative means that we have a left tail on our distribution. And the fact that we have a positive skewness means that we have a right tail in my distribution. Now, consider the case of the kurtosis. Kurtosis measures the tailedness of the distribution, and it's very useful to analyze the peak, the tails, and the presence of outliers. Overall, the distribution can have a steeper or a flatter peak and a longer or shorter tail. Let's have a look at it. Based on the value of the kurtosis, we can classify a distribution in one of three types. It can be platykurtic, leptokurtic, and mesokurtic. A platykurtic distribution is the one that has a flatter peak and shorter tail. The leptokurtic distribution has a longer tail and steeper peak, whilst the mesokurtic distribution has a close to zero or zero kurtosis. Taking the case of these 4 examples, what we can see is that this is a more normal distribution, so this is a mesokurtic distribution, and the kurtosis value is approximately 0. The uniform distribution has a negative kurtosis, and this means that this is a platykurtic distribution, in the sense that it is a more uniform distribution with no tails or with very small tails. The same thing happens with the semicircle distribution that also has no tails, but this is not as uniform as the uniform distribution that we showed here. And finally, we have a leptokurtic distribution that is steeper and has longer tails. To conclude, let us take the example of the forest fires dataset. We are here looking at the variables FFMC, ISI, and the wind. As we can see, the distribution of FFMC has a long tail to the left, so its skewness is negative, and it also has a high value because it has a long tail to the left. And it also has a high kurtosis value, thus it is a leptokurtic distribution, meaning that it has a steeper peak. When we look at the distribution for the variable IZ, we can see that its skewness is positive, meaning that it has a tail to the right, but it's not as big as the skewness of variable FFMC, meaning that its tail is not as long as the tail of variable FFMC. And also we see that it has a positive kurtosis, meaning that it also has a steeper peak, but again, not as steep as the peak of variable FFMC. And finally, we have the variable wind with a skewness close to 0, meaning that it almost has no tail, though we can see that it has a slightly positive tail here, which is indicated by the positive sign of the skewness. However, the small value shows that it has a short tail, and the kurtosis very close to 0 also shows us that this distribution is close to a normal distribution. Thank you for watching, and see you in our next and last class of this course.